5-1. Curve sketching. We're going to look at the extrema. We're going to look at points of inflection. And they are sketches. They are not perfect drawings, but we're trying to get the gist and get a sense of what they may look like in all likelihood based off of, the numbers. To be honest with you, this is something we just started talking about in Algebra 2 yesterday, the last couple days. What the numbers do to the graph. How do they affect the graph? And you guys are much more skilled at that than the Algebra 2 kids because they're just starting to learn that. But at our level, we do it much more in-depthly. And rather than looking at just, linear functions, which is what we're starting with in Algebra 2, we look at much more complicated type of graphs, okay? So there's a little step-by-step process. This is in your book. I'm going to go through them one step at a time. You can certainly screenshot those steps and put them in and save yourself a little bit of trouble in terms of writing if you want to. Of course, you can always write them. All right, so the first thing we're going to do is we're going to state the domain. Okay, we need to make sure we know where asymptotes might be. We need to be sure we know where holes might be, where jumps might be. And identifying the domain is going to help us accomplish that. All right, the second thing is you're going to want to reduce. When you reduce your function, it's going to make it easier to graph. If it's reducible, it's not always going to be reducible. But if you can reduce it, I suggest that you do that. The reason we state the domain first is that the holes, the asymptotes, the jumps still exist even if after we reduce it. Those still are in play. Okay, so then we're talking about vertical asymptotes and holes. That's what we were doing 1 and 2 to begin with, is to figure out where those are. Find the intercepts, just because those are always good points. Those are nice points usually to graph. Of course, x-intercepts when we cross over from negative y's to positive y's or positive y's to negative y's, that's going to tell us something about the slopes and increasing, decreasing, potential minimum and maximums, that kind of thing. Find end behavior, so horizontal asymptotes or other types of behavior, whether it continues on and on forever to the right or to the left or up or down, that kind of thing. Or if it flattens out, for that matter, and becomes constant. Okay. Increasing and decreasing intervals, and then find the minimum and maximum. Okay, so when it says show a first derivative number line, that's where we're talking about positive on this side, negative on that side, and that kind of thing. And then concavity based on the second derivative. So now we're making a second derivative number line so that we can determine points of inflection. And then you're going to graph. And you're going to sketch it, and it's going to be one of those things, I don't know about you, but when I try to sketch it, I never get it right the first time. I'm never satisfied with my first little sketch. I always feel like I can make it curve a little bit better, or find a spot where there's going to be a horizontal tangent a little bit better, or get it a little bit closer to the asymptote, that kind of thing. So don't expect to just knock it out on the first try. I don't feel like that's it's usually going to happen. Now, if it does happen and you're like, man, that's really good, and you nailed it on the first, you get that sense of satisfaction, right? Because that usually doesn't happen. If you do, of course, that's great. If that happens to you, then you're amazing. All right, so here's the question we're going to do. This is the first example that we're going to go through, and I think the only one. Yeah, this is the only one we're going to go through. They give us a lot of information here, okay? They give us the function itself, they give us the first derivative, and they give us the second derivative. That saves us a lot of time, right? If in a problem like this, if you were to find the first derivative of this using quotient rule, lots of opportunities for mistakes. Ooh, that reminds me, I'm going to hand your test back later. Speaking of opportunities for mistakes. Yeah, that's why I remembered it, because there's some of you that messed up the quotient rule a little bit on the test yesterday. So yeah, that's why I remembered it. And so it's nice that they give us all three, okay? And so what we do from there, and they have this little, it's like what's the word I'm looking for? It's like a formatting, where it lets you kind of remember all the stuff that you need to put in there, okay? And so this bothers me a little bit, and I will change it um, it makes it seem like, I just wish it was a D instead of do. That's the only thing I don't know. D for domain. It's just, I see D-O, and I don't think domain, I think do. And I'm like, do. Like, what? I don't get it. So anyway. So we're going to find the domain, vertical asymptote, any holes that might exist, x-intercepts, y-intercepts, EB. What do you think EB stands for? End behavior. Very good. Relative maximum points, relative minimum points, and private investigators. Points of inflection. Okay, give it a shot, and let's see what you end up with, and then we'll come back together and try to go through it together and see if we got the same things. Just remember what we are graphing f of x. Okay, these other things are going to allow us to get information. We are not graphing the first derivative or the second derivative. We are just graphing the first derivative, or the function f of x. Just graphing f of x. It might be helpful for you, not necessarily, if you think of this denominator as x minus 1 quantity squared. Maybe that makes your life a little bit easier. And you can also tell that when you look at the first derivative and the second derivative that it's going to have to be squared based on the denominators. Is finding all this information first. All this information first tells us a lot, and it creates boundaries, and it tells us restrictions, and it starts helping us form what the shape might be looking like, okay? And what's important is that all of this information gives us some information about what the graph is going to look like. So that's why I think this formatting, this skeleton, I think this is good. I like this. So we're going to go one at a time. And again, until we get down to here, we're just focused on the actual function. All right, so the domain, our only restriction is what? What can't happen for the domain? Yeah, x cannot equal 1, because that would make the denominator 0. My domain, x cannot equal 1. It could equal anything else. Okay. Can this be reduced? Can I do anything with this? I mean, this is x minus 1 quantity squared. I could factor out a 3, but I'd be left with a fraction. So I'm not going to get another x minus 1, so that's important. All right, vertical asymptotes. The domain restriction and the vertical asymptotes are basically the same thing, right? So I have a vertical asymptote at the line x equals 1. Do I have any holes here? No, because I couldn't reduce it, right? If the x minus 1s on the bottom went away after reducing it, then fine, we'd have to consider a hole. But because nothing's reducible here, there are no holes. X-intercepts, now we're talking about making the numerator equal to 0, because an x-intercept means y equals 0. So 3x minus 2/3 would have to equal 0, which means x would have to be 2/3. And the point is 2/3 0. All right, so we have the x-intercept 2/3 0. The y-intercept, now I'm plugging 0 in for x. And so that is 0, -2. Because if I plug 0 on the bottom, I just get a 1. And so then I get -2. All right, end behavior. How do we figure that out? Yeah, let's find out some horizontal asymptotes. Now, there's some rules, right? What's your first kind of go-to when you're thinking about horizontal asymptotes?
If the degrees are the same, then
just looking at the degrees of numerators and denominators, right? And those tell us different things. And then you get into those rules, right? So if the degree on the bottom is bigger, then we know there's a horizontal asymptote at the line y equals 0, okay? If the degrees are the same, you got to divide the coefficients. Now in this case, I have degree of 1 on top, degree of 2 on the bottom, so I know that I'm going to have horizontal asymptote at y equals 0, okay? So just kind of remember those rules. When the degree on the top, I guess I did mention that one. When the degree on the top is bigger than the degree on the bottom, what does it mean?
none.
There are none, right? There are no horizontal. So there's really only 3 rules that go along with that for horizontal asymptotes. All right, so now we get into max and mins, okay? And when we get into max and mins, we're going to look at the first derivative, okay, since they give it to us. All right, so we have to consider possible critical numbers. And what are my possible critical numbers for the first derivative? What's going to make the top 0? 1/3. What's going to make the bottom 0? 1. So my possible critical numbers are 0 and 1. Or sorry, 1/3 and 1. Okay. So I went ahead and already made my number line. Right, so I've got my 1/3, I got my 1, I've tested them out. All right, so when I go from negative to positive, minimum or maximum? Min. Positive to negative. Okay, max. Now, so what I just need to do is plug those values in, plug 1 in, and that'll give me my max. Plug 1/3 in, that'll give me my min. And when you do that, what's the issue? What's the issue here about this max? Right, 1 does not exist. Okay, there is a vertical asymptote at 1. So the graph is not continuous from this region to this region. So before I go ahead and claim that 1 is a maximum, I have to revisit my domain and my asymptotes and go, oh yeah, wait, 1's a problem, even though we still test it. So the truth is there is no relative max. Because of the only place it could happen is at 1, and 1 can't happen. So in either case, we still have to test it, right? We still have to test the undefined values on either side and see. Now, should we have maybe been like, all right, look, there's going to be an asymptote right here. There's no way. Yeah, that's correct. All right. Min, are we okay on a min? Yeah, we're okay with a min. So I plug 1/3 in, and we get 9/4. There's that 9/4 again. That was also on your test. All right. Is it negative?
Yeah. Because it's -1 over 4/9.
Correct. Should be negative. Hopefully I graphed it right. Now I'm worried that I didn't graph it right. Maybe I did, and I'm hoping I just left the negative sign off. That's what I'm hoping. I don't know if I did or not. We'll find out. We'll find out together. That's frightening. Here we go. Okay, so then my second derivative. And I'm going to keep writing this one in. Second derivative. Okay, so now I'm looking at 0 and also 1. Okay, again, critical numbers for the second derivative. Notice there's no sign change, and also still we have the situation with the asymptote. Okay, so the only place we're going to be concave down here, we're going to be concave up the rest of the way. All right, so my point of inflection then is at 0, and we already know that that's the y-intercept because we already had figured that out from before. All right, so here's where I like to start. Okay, I like to put my asymptotes in first. Okay, anybody else like to do that first? Okay. I like to put those in first because they create those boundaries for you so you know where you shouldn't be drawing anything. Okay, so I know that I have a vertical asymptote here at x equals 1. We know that we have a horizontal asymptote here at y equals 0. Okay. That's the first place I like to start. Next, what I like to do is take the points that I've already found out, like all these points here. We got a point here, we got a point here, we got a point here, and I like to graph them all. Let's see if so I guess now we're going to find out if I graphed it in the right place. I did. Wow, that's so... So here's one of the things that you have to know about horizontal asymptotes that maybe you don't know. Okay, that the graph can cross the horizontal asymptote. The horizontal asymptote is about end behavior. Okay, that's where we're really paying attention to it. So that boundary where the graph is coming close to the line y equals 0, we're really worried about it outside on the ends of the graph. okay? It can cross the horizontal asymptote in the middle. Vertical asymptote, that doesn't apply to. They never cross the vertical asymptote. But that always comes up in Algebra 2 as well. The kids ask the same thing. Wait a minute, I thought it's a force field and it can't go across it. Like, I get it. Yeah, well, we don't, because that's how I talk about like that a little bit. But we don't talk about end behavior in Algebra 2, okay? We don't talk about that. And so every year some kid asks me about it because they're smart enough to figure out, like, hey, this is a problem. Why is this okay? And we just have to remember that horizontal asymptotes apply to end behavior. A lot of the time it won't cross it anyway, but in this case, obviously it does. Okay. I feel so much better about the fact that I graphed the point in the correct place. All right, next. So now we got to start using the information and figuring out, like, where do I go? Okay. And like I said, maybe you want to test some points because we probably have a graph over here somewhere, but without a lot of information, you might want to create a little bit of a table and plug some values in. All right, but before we do that, I'm going to focus on this side. Okay, let's focus on this side. We know that that we have a concavity change right here at 0. Okay, we know that from here to here it's concave up, so we can see that it goes down and then it comes back up, and it'll probably go up forever right along this. Okay, and so the first thing that I would do, because that's the easiest thing to kind of figure, is draw that. Okay, so I connect those points. I have my concave up, right? It's easy to tell from those points, and then it has to come back up, and then it rides along the asymptote. All right. The next part is understanding that since this graph, because of this asymptote, is it can't cross it because now we're talking about end behavior. It's gonna ride along that asymptote. The trick is you got to make sure that you make it concave down. Now, it doesn't have to be significantly concave down, and if you want to plug some points in to try to figure out, where it's going to be exactly, you can, or you can quote unquote sketch, and that's not a big deal. All right, and so for here, the trick is making that ensure that it's concave down the whole way, meaning again the tangent lines are above the graph, and so here's what I came up with. See if you got something. So I got my little curve. Tangent lines are all going to be above it. Right at this point, now we are concave. How many had something like that? Okay, very nice. So again, for the last part, I know it has to be concave up. That's for sure. Okay, and when we don't really have anything here, we can assume that it's probably going to look like this, right? It's going to ride up along that. It's going to ride up along this. But just to be safe, at least this is what I did, and you certainly can do whatever you want. But I picked some, and you're going to be like, why did you pick these numbers? And I'll explain why in a minute. I actually picked some points. I know you're like, 4/3, really? That's what you're going with? Well, you picked 3/2. The reason I picked 4/3 is because then the 3 is going to get knocked out, right? It's going to be 4 minus 2 on top. Obviously, 18 in 4/3 is just beyond this line, is way up here somewhere. So that kind of, for me, validates the idea that it's going to climb here. And this one here, 4, just because that was the last point on my graph, that's the reason I picked 4. On this grid, that was the last one, and I wanted to see where it needed to be. That's why I chose 4. Because if you draw it down too low, it's not as accurate as it could be. And that's kind of ultimately what we're all trying to do, is come up with the best curve or the best sketch. And so, like many of you, you're not going to just settle for a sketch. You're going to want to try to make the best sketch. And so at some point, maybe throw a point in there and try to figure out what it's going to do. And eventually this is going to run, if I had more grid, it would get a lot closer. That's why I didn't make it close, because I knew that at 4, it's just not close to the asymptote yet. It'll get closer as we get further to the right, and that's why it looks like that, okay?